Greetings, AP Stat. Welcome back to Chapter 14. This is the second part. We're going to be talking about something called conditional probability. And this is about the point where probability starts to get a little bit more challenging. So buckle up your seatbelts. Here we go. So to the right is a contingency table. We have a two-way table that gives the counts of what a sample of senior high boys and girls make their goal, whether grades or being popular or excelling in sports. What is the probability that, given that the student is a girl, assuming we are only considering the girls, her goal is sports? Right? Now, this is a different question than we've seen before. This is not just asking what is the probability that we're dealing with a girl whose interest is sports. No, this is given we are only considering the girls, what then is the probability that her goal is sports? This is a different question than we've seen before. The probability of an event B happening, given that some other event A has happened or is assumed true, is called the conditional probability. And we call it conditional probability because it's the probability that some event, we'll call it B, happens on the condition that A is assumed to be true or has already happened. If we assume an event A has already happened, that's why we use the first letter to talk about it, because it's already happened, or we already assume it to be true. What are the odds that B also is going to happen? That is conditional probability. And we can find the probability of B given A, B on the condition of A already happening or being assumed to be true, using this formula. The probability of B given A is the probability that they both happen divided by the probability that A happens. So we're only considering the circumstances in which A happens, and we ask ourselves, what are the odds that B happens as well? That's why this formula works. So let's get to our solution, shall we? The probability of sports given girl. Probability of sports, considering we are only talking about the female students, is the probability of girl and sports divided by the probability of girl. Probability of B given A is the probability of A and B divided by the probability of just A. So substituting, we would get, well, there are 30 girls who are also interested in sports out of the total 478. So that's the probability of choosing a girl whose biggest interest is sports. And we divide that by the 251 girls divided by the total of 478. That's the odds of choosing a female student, a little over 50%. And that would equal 30 over 251, which the value is a little interesting. Is this 30 referring to that 30? Is this 251 referring to that 251? Well, yes, arithmetically so, and we'll find it's also true of something going on in the table. We'll see in just a moment. If we divide fractions, you remember from arithmetic, from algebra, from all the math you've taken in junior and senior high, you multiply the numerator, this 30 out of 478, over the reciprocal of the denominator, or should I say by the reciprocal of the denominator. Multiply the numerator by the reciprocal of the denominator to divide fractions. So you have the numerator, 30 over 478, times the reciprocal of the denominator, means that the 478s are going to cancel, leaving 30 out of 251. And this makes sense. Consider what I'm about to do in this table over here. I'm only considering the female students, and specifically concerning the likelihood that they have a biggest interest in sports, that's their goal. So if I consider the number of girls who are interested most in sports, and I divide that by the total number of girls, that gets me my probability. So I am living in the world of the female student, And within that world, within that row, I am considering this cell right here, the intersection of girl and sports. So you can use this formula, but if you're given a two-way table, whatever is what you are given, whatever is your A in this context, you live in that world. You're only considering that row or column. We're conveniently given a total, so we can use that. If we weren't given a total, we just add up the values in our row or column. And then we find the specific cell in the column that pertains to our special interests, not just the female students, but the female students who are interested in sports. So you live in a particular world, as it were, and you select from within that world the category you're most interested in, or should I say the cell that you're most interested in. And then the division is really easy. So if you're given a two-way table, you are given a gift, and absolutely use that gift. Here's another example, and we don't have a two-way table for this one, but the formula turns out to be really, really convenient here. Our survey found that 56% of college students live on campus, 62% have a campus meal program, and 42% do both. That's from our prior video. While dining in a campus facility open only to students with meal plans, you meet someone interesting. That'll happen in college. What is the probability that your new acquaintance lives on campus? So we're trying to find the odds that we live on campus given that we only are dealing with people who have meal plans. Okay, so how would we solve this? Well, here we go. We're going to use our abbreviations here. We're going to let L be living on campus and M be having a campus meal plan. The probability a student lives on campus given that the student has a meal plan would be probability of L given M. All right, now we use the formula. Probability of both divided by probability of the meal plan. We want to live in the world of the meal plan and consider what are the odds that we also live on campus, okay? So the odds of doing both would be 42%. We get that from right here. And the odds of having a meal plan is 62%. We get that from right here. After a little division, we get 0.677. So there's a probability of about 0.677 the student with a meal plan also lives on campus. All right? And interestingly, this is a higher probability than for all students. 56% of all students live on campus, but if we only care about the students with the meal plan, the odds of them living on campus goes up, and I'll let you think about why that might be true. All right, now we cannot finish a discussion on conditional probability without discussing independence, one of the two biggest terms in statistics. The first being significance, which we'll talk about really the last third of the year, and independence. Those are the two biggest terms in statistics, if you ask me. So recall that two events are independent if the occurrence of one does not affect the probability of the other occurring as well. So in other words, A and B are independent when the probability of B given A is equal to the probability of B. In other words, the probability of B occurring doesn't depend on whether or not A happens. This is the probability of B given that A has happened. This is the probability of B in the general sense. So if these are equal, it means it doesn't matter whether A has happened, B is just as likely. And that is an algebraic, if you will, rendering of the concept of independence. It doesn't matter whether A is assumed or not. B is just as likely. B does not depend on A happening. The odds don't change, hence they are independent. Cool fact about independence, and I'll let you think about why this is true as well, independence is symmetric. That means that if A is independent from B, then B is independent from A. This sentence is a good example about how not to use a comma. Terrible. Moving on. Unless we are told otherwise, assume that if probability of B given A and probability of B are equivalent to, not perfect, but within 2 decimal places, or to the nearest whole number percent, A and B are independent. All right, so sometimes independence is perfect because we're dealing in the world of math class. In the real world, independence is kind of like, these events are almost independent. Probability of B given A and probability of B are so close to each other that we'll say they're just about independent. That's what's going on in the real world. So we have standards here, but if the quantities probability of B and probability of B given A are within 1% of each other or accurate to 2 decimal places, A and B are essentially independent. That'll be our rule. And on the AP test, it will be very clear whether events are independent or not. You're not going to have a guessing game on your hands. All right. So, question number 1. Determine whether sports and girl are independent. And then question number 2, determine whether grades and girl are independent. Okay, so I'm going to do number 1 here, and I'll leave number 2 to you. Here comes problem number 1. Probability of sports given girl. All right, so we're going to assume we're only talking about the female students. What's the probability that those students are interested in sports as well? That is 30 out of 251. You already knew that. That comes out to about 0.12 approximately. It's a 0.19 and then something bigger than 5, and so we just round up to 0.12. I showed 3 places because we want to be within 2 decimal places accurate, so I took it out to 3 just so it would be crystal clear. But probability of sports is 90 out of 478, which is 0.188. So sports given girl is different than sports in general, which means that your appreciation for sports does pretty firmly depend on whether you're a girl or a boy, at least in this survey, in these survey data here. So sports and girl are not independent. 0.12 is very far away in terms of determining independence from 0.19 approximately. That's way off. Those events are not even close to independent. So you try number 2 for yourself, see how you would set it up, find those probabilities, and determine whether you think those events are independent. Unpause the video when you're done. Okay, I'll assume we're ready to continue. We're going to determine whether grades and girl are independent events. So the probability of grades given girl is equal to 130 out of 251. And that's about 51.7%. But probability of just grades in the general sense is 247 out of 478, which is 0.518. That is accurate to within 1%. All right, we got 0.517 as opposed to 0.518. Is it perfect? No, but these are pretty reasonable data you might be able to come up with in the real world. That a 60 and 30 split might seem a little contrived, but everything else appears to be pretty similar to what you might find in real world data. And in these data right here, it's not perfect, but it's within 1%. So grades and girl we can consider independent. So we're going to end our lesson today with an interesting question from our book with familiar data, of course. Our survey told us that 56% of college students live on campus, 62% have a campus meal program, and 42% do both. And the question is, are living on campus and having a meal plan independent? And, blast to the past, are they disjoint? As a reminder, disjoint means that if 2 events are disjoint, they cannot happen at the same time. Independent means the occurrence of one does not affect the likelihood of the other. So again, disjoint is cannot happen at the same time, and independent is the occurrence of one does not affect the probability of the other. Those are very, very different. Okay? So think about it. Are living on campus and having a meal plan independent, and are they disjoint? Take a moment, try and solve this one on your own, or these two rather, on your own, and unpause the video when you are done. Okay, let's get to it. So, here's the book's answer, and I think it's very thorough and helpful. Let L be the students that live on campus and M be the student have a meal plan. If these events are independent, then knowing that a student lives on campus doesn't affect the probability that he or she has a meal plan. So we'll check to see if meal plan given living on campus is the same as having a meal plan in the general sense. Probability of meal plan given living on campus is probability of both, which is our 42%, over the probability of living on campus. That's 42 out of 56, which is an even 75%. But as we see in our problem, the probability of having a meal plan is 62%, and last I checked, that is different than 3 out of 4. Because 3 out of 4 is not the same as 62%, the events are not independent at all. Students who live on campus are more likely to have meal plans. Living on campus and having a meal plan are not disjoint either, and one number will do that for you. This word both destroys the possibility of disjointness from these two variables, living on campus and having a meal plan. If both can happen, the events are not disjoint, and that apparently happens nearly half the time. So these events are very, very far from disjoint as well.